So analysis, per se, what makes it different than other types of mathematics is that analysis is primarily concerned with the measurement and the control of the distance between things. Those things might be numbers, they might be functions, they might be sequences, they might be all kinds of different stuff. But if you're measuring and controlling distances, you're probably doing some flavor of analysis in mathematics. And all semester we've been talking about absolute values of differences of real numbers being bounded, less than some epsilon or some delta or whatever. And secretly what we've been doing there is controlling the distance between those two real numbers. So in this video we want to verify that the more general notion of metric and metric space that we developed in the previous video actually lines up with the kinds of absolute values of differences that we've been talking about all semester. So we'll show that the absolute value of the difference of two real numbers actually satisfies the properties of a metric space. And then after that, in the video that follows this one, we'll look at some other examples of metrics that might be of interest to us, that will tee up our ability to use metric spaces to both generalize the definitions that we've seen previously in more specific cases in analysis, and then implement those more generalized definitions to do things like, for example, show that a sequence of functions converges in some sense. So let's see what that looks like. So first and foremost, let's show that the absolute value of the difference of two real numbers actually defines a metric on the set of real numbers. So to do that, we have to show that these four properties are satisfied. Right? The first one is the non-negativity property. Is it true that the absolute value of x minus y is greater than or equal to 0 for all x and y? Well, yeah, that's true. This is one of the properties of absolute values that we learned, because absolute value is measuring the distance of a real number from 0. That distance is never going to be less than 0. So for sure, the non-negativity property is satisfied by the absolute value of the difference. The second property is the non-degeneracy property. That should tell me that the distance between x and y is 0 only in the case where x is equal to y. So it's never possible for me to take two different real numbers in this example and have the absolute value of their difference be equal to 0. So is it true that if the absolute value of x minus y is equal to 0, then we can conclude x is equal to y? Well, if the absolute value of x minus y is equal to 0, that means that x minus y is either 0 or it's the opposite of 0. Except that 0 and the opposite of 0 are both the same thing. They're 0. And so that means that x minus y must be equal to 0, and hence that x must be equal to y. So we have non-degeneracy. The only way that the absolute value of the difference of two real numbers can be 0 is if those two real numbers were the same to begin with. How about symmetry? Is it true that the distance between x and y is the same as the distance between y and x? Is the absolute value of x minus y the same as the absolute value of y minus x? Well, sure. What is the absolute value of y minus x other than the absolute value of -1 times the quantity x minus y? And we happen to know, from our properties of absolute value that you learned back in algebra, that the absolute value of a product is the product of the absolute values. Absolute value is a multiplicative function. It's an example of what we call in algebra a norm function. And so I can split out that absolute value of -1 times the absolute value of x minus y. But what is the absolute value of -1? It's just 1, and multiplication by 1 is invisible. So the absolute value of y minus x is exactly the same thing as the absolute value of x minus y. Okay, so the triangle inequality is going to be the one that's going to require the most thinking. And we won't go through all of the 6 different cases that would be necessary to prove that this is true. Instead, what we're going to do is use a different version of the triangle inequality, the one that we've already met earlier in our analysis journey. So how do I show that the absolute value of x minus z is less than or equal to the absolute value of x minus y plus the absolute value of y minus z? Well, let's remember what version of the triangle inequality we learned a long time ago when we first started studying absolute values in analysis. The original version looked something like this. The absolute value of a plus b is less than or equal to the absolute value of a plus the absolute value of b. And on its face, it doesn't seem like this inequality should help me to prove the inequality that we're trying to establish right here. Because after all, the left-hand side of this inequality has a plus in it, and we don't have any pluses going on the left-hand side, at least. You don't have any pluses inside of absolute values. Maybe let's put it that way. So I want to think about this inequality just a little bit differently. What I want to do is say, how can I make this left-hand side of my inequality look more like the absolute value, not of a sum, but of a difference? Well, instead of adding b to a, I could instead subtract the opposite of b. If I subtract the opposite of b, now I really am measuring a distance, right? According to our definition of calling this a distance function. What I'm really doing is I'm measuring the distance from A to minus B. And so my little triangle diagram, we're going to draw a lot of these diagrams as the semester goes along for exactly the reason that I'm going to draw it here. I want to know something about the distance from A to minus B. And so to find out something about the distance from A to minus B, I'm going to take a detour. Instead of going directly from A to minus B, I'm going to make a stopover at 0. So I go from A to 0, then I go from 0 to minus B. And I can label the distances on all three sides of this triangle. On the bottom side, the distance is the absolute value of A minus the opposite of B, in other words, the absolute value of A plus B. But on the other two sides, we have the distance from A to 0 and the distance of minus B to 0. Each of those is respectively the absolute value of A and the absolute value of minus B, which is the same thing as the absolute value of B. So this little diagram sort of tells me that if I don't know how to control one of these distances, I should try taking a detour. And in my detour, if I can control the other distances, then the triangle inequality will let me control the one that I didn't know. This is going to be a very common strategy in the whole rest of our analysis journey. And it's one that I sort of wish I'd started talking about much earlier in this series of videos, because it could have helped us in a lot of proofs to conceptualize what it was that we were doing. So this is a really underrated skill right here. So how can we use a diagram like this to establish the triangle inequality for the metric absolute value of x minus y? Well, we're going to use, and here is the key to using one of these diagrams, we're going to use an adding and subtracting trick. In other words, we're going to add and subtract the same quantity so that we haven't done anything at all, but by doing so, introduce a new arithmetic, and we're going to introduce a new addition inside of my absolute value that's going to let me use the ordinary triangle inequality to split it apart. So what do I mean? Well, what I'm trying to find out something about, and I don't know how to control here, is the absolute value of x minus z, which is the distance between x and z. So I don't know how to control that. I need to know that it's less than or equal to something, right? And so to figure out what it's less than or equal to, I'm going to try to take a detour and put an intermediate stop in between x and z. I'm going to call that intermediate stop y. And the detour that I take is going to be reflected in the fact that I'm going to add and subtract, really subtract first and then add it back, the number y inside of my absolute value, in between my x and my z. So here's what it looks like to employ this trick. I take the absolute value of x minus z, which I'm interested in finding an upper bound for, so I want to control this thing from above. And I don't know how to do that, so I add the stopover at y, and I subtract y and add y in the same spot in the middle. So instead of x minus z, I have x minus y plus y minus z. I haven't done anything at all to the value of this expression because I've really just added 0 to it on the inside, right? But by introducing a plus inside of my absolute value, now I can use my ordinary triangle inequality, which tells me the absolute value of a sum is less than or equal to the sum of the absolute values. And if I use that ordinary triangle inequality, I can split this up into being less than or equal to the sum of the absolute value of x minus y, that's the distance from x to y in my triangle diagram, added to the absolute value of y minus z, that's the distance from y to z in my triangle diagram. And in doing that, I have actually immediately established the triangle inequality that we were aiming for. So the real numbers, when we equip them with the absolute value of a difference, they form a metric space, right? This function, the absolute value of the difference of two real numbers, actually satisfies everything that a metric function would need to satisfy. So what's the moral of this story? The moral of the story is that, yes, this is one particular example of a metric that we've been working with all semester so far. But why we're interested in metric spaces is that a lot of the times that we were working with absolute values of differences in our previous definitions, we were really secretly working with a metric. And many definitions from our ordinary one-dimensional analysis will generalize to the more general context of metric spaces. All we have to do is replace the specific absolute value of a difference of real numbers with the more general, or depending on the case, specific but different metric, the distance between two things. So as an example, what would it look like to write out a definition of what it should mean for a function from one metric space to another metric space to be a continuous function? Well, the first thing we'd do is write out the definition that we know from one-dimensional, plain, ordinary, real analysis of one-variable functions. Let's let x and y be metric spaces and f be a function from x to y. Then what it means for f to be continuous in the ordinary rendition at a point x naught is that For all epsilon greater than 0, there is a delta greater than 0, such that whenever the distance between x and x naught is less than delta, and distance measured by absolute value in the ordinary case, then the absolute value of the difference of f of x and f of x naught is less than epsilon. So to make this into the more general definition for metric spaces, I just want to replace the particular absolute value of a difference with the more general metric measured distance between those two things. So here I have the absolute value of x minus x naught being controlled less than delta. What I want instead is I want the distance measured by a metric between x and x naught to be less than delta. And I'm using the metric that came from the metric space x because that's where the points x naught and x came from. So I'm using the d metric to measure this distance. Then when I go to convert the absolute value of this difference into a metric statement, I would want to use the metric over here that reflects the fact that f of x and f of x naught are both points not of the space x, but of the point of the space y, right? They're part of the codomain, not part of the domain of the function f. And so since these points live in the space y, the right metric to measure the distance between them is the metric that we've equipped the space y with, namely the metric we're calling e. So instead of the absolute value of f of x minus f of x naught, we have the e metric distance between f of x and f of x naught. And just by trading out those absolute values of differences for metric distances, we now have a definition of what a function from one metric space to another metric space needs to satisfy in order to be called a continuous function. And in the case where both my domain and my codomain are the real numbers with the absolute value metric, this reduces down to our ordinary definition of what it means for a function of one variable, one real variable, to be continuous. So this generalization process works for nearly any of the definitions that we've written down in analysis so far that have used absolute values. Right? That the reason that we use absolute values is as a surrogate for measuring distance. And when we measure it in a more general fashion, our definitions can generalize pretty immediately like this.